Welcome to the Sleepy Station. Get comfortable and relaxed. We're about to set off on an adventure into space, so when you're ready, close your eyes and let's go. Our journey begins at the very edge of what we can see, where light itself grows tired from traveling so far across the universe. There are places in space where starlight has been journeying for so long that the stars themselves may no longer exist, yet their glow continues onward through the darkness, a gentle whisper from the distant past. Each photon that reaches us has sailed through an ocean of emptiness, undisturbed for billions of years, carrying with it a story from when the universe was young and different. In the depths of space, there are clouds of gas and dust that stretch across distances almost too vast to comprehend. These nebulae drift slowly through the galaxy, turning and folding in on themselves over millions of years. Within them, new stars are being born, their light beginning to peek through the surrounding material, like dawn breaking through morning mist. The process is gentle and slow, a cosmic dance that has been repeating itself since the first stars emerged from the primordial darkness. Consider the curious nature of dark matter, that invisible substance that makes up most of the matter in the universe. We cannot see it, cannot touch it, yet we know it is there by the way it pulls on the things we can see. Galaxies spin faster than they should, held together by this unseen presence. It passes through the earth, through you, through everything, as though we are ghosts to it, and it is a ghost to us. Scientists continue to search for its true nature, peering into the darkness with increasingly sensitive instruments, hoping to catch a glimpse of this elusive cosmic companion. The moon, our closest celestial neighbor, holds mysteries of its own, despite being the only other world that humans have walked upon. Deep beneath its dusty surface, there are patterns in the rock that suggest ancient volcanic activity, creating lava tubes that might stretch for miles in the lunar darkness. These underground passages remain unexplored, potential shelters from the harsh radiation that bathes the airless surface. The moon continues to drift slowly away from Earth, moving about 1.5 inches farther each year, a gradual goodbye that will take billions of years to complete. Venus, our sister planet, spins in the opposite direction from most other worlds, rotating backwards on its axis. A day on Venus is longer than its year, the thick atmosphere moving in great sweeping patterns that carry heat from the day side to the night side. The clouds themselves rain sulfuric acid that never reaches the ground, evaporating in the intense heat of the lower atmosphere. Yet high in those same clouds, there is a layer where temperatures and pressures are almost Earth-like, a potential refuge in an otherwise inhospitable world. Mars waits patiently in its orbit, its rusty surface marked by the scars of ancient rivers and seas. Once, long ago, water flowed freely across the Martian landscape, carving channels and filling basins. The planet held onto a thicker atmosphere then, one that could support liquid water at the surface. But over time, the solar wind stripped away those protective layers, and the water either froze into the soil or evaporated into space. Now, we send our robotic explorers to search for signs of that ancient past, hoping to find traces of life that may have once flourished there. Jupiter, the giant of our solar system, spins so rapidly that it bulges at its equator, its clouds racing around the planet in colorful bands. Deep within those clouds, lightning bolts more powerful than any on Earth flash between layers of different composition. The Great Red Spot, a storm larger than our entire planet, has been raging for hundreds of years, slowly shrinking but showing no signs of stopping. Scientists wonder what drives this persistent tempest, what balance of forces keeps it alive decade after decade. Beneath the icy surface of Europa, one of Jupiter's many moons, there may be an ocean of liquid water kept warm by the constant kneading of tidal forces. The same gravitational pull that creates tides in Earth's oceans flexes Europa's interior, generating heat through friction. This hidden sea could be twice the volume of all of Earth's oceans combined, a dark, subsurface realm that has never seen sunlight. If life exists there, it would have evolved in complete darkness, perhaps clustering around hydrothermal vents on the ocean floor, much like the strange creatures found in the deepest parts of our own seas. Saturn's rings, those beautiful bands of ice and rock, are surprisingly thin. Though they stretch across hundreds of thousands of miles, in most places they are only about 30 feet thick, like a cosmic sheet of paper wrapped around the planet. The particles that make up the rings range in size from tiny grains to house-sized boulders, all orbiting in an intricate dance. The rings may be the remains of a moon that wandered too close and was torn apart by Saturn's gravity, or they might be leftover material from the planet's formation, pieces that never quite came together. Titan, Saturn's largest moon, is the only moon in our solar system with a substantial atmosphere. Thick orange hazes hide the surface from view, and liquid methane flows in rivers and collects in lakes, creating a hydrological cycle similar to Earth's water cycle, but playing out at temperatures hundreds of degrees below freezing. Rain falls from Titan's clouds, slowly, in the low gravity and thick air, taking hours to complete its journey from sky to ground. The surface itself may have a layer of soft organic material, a sort of cosmic snow made from complex carbon compounds. Farther out in the solar system we find Uranus, tipped on its side so that its poles take turns pointing at the sun. This unusual orientation may have resulted from a massive collision early in the planet's history, an impact that knocked it over and set it spinning in its current configuration. The planet's atmosphere contains methane, which absorbs red light and gives Uranus its blue-green color. Beneath the atmosphere, there may be an ocean of hot, dense fluid containing water, methane, and ammonia surrounding a rocky core. Neptune, the most distant of the major planets, has winds that howl faster than the speed of sound on Earth, whipping around the planet at over 1,000 miles per hour. The source of energy that drives these fierce storms remains something of a mystery, as Neptune receives very little warmth from the distant sun. The planet appears to generate its own internal heat, though we are not entirely sure how. Like Uranus, Neptune's deep blue color comes from methane in its atmosphere, but Neptune's color is more vivid, more intense, suggesting additional substances that have not yet been identified. Pluto, once considered the 9th planet and now classified as a dwarf planet, surprised everyone when our spacecraft finally visited it. Instead of a dead, cratered world, we found a complex surface with vast plains of frozen nitrogen, mountains made of water ice as hard as rock in the extreme cold, and possible cryovolcanoes that might occasionally erupt with ice and ammonia. The heart-shaped region on its surface, informally named Tomba Regio, appears to be geologically active, its surface refreshing itself over time. Even at the edge of the solar system, billions of miles from the sun's warmth, Pluto remains dynamic. Beyond Pluto lies the Kuiper Belt, a vast ring of icy bodies that orbit in the outer reaches of our solar system. These objects are remnants from the formation of the planets, pristine samples of the material that built our cosmic neighborhood. Some are small, barely more than dirty snowballs, while others rival Pluto in size. They orbit in the cold and dark, undisturbed for billions of years, waiting patiently. Occasionally, one is nudged inward by gravitational interactions, beginning a long fall toward the sun, heating up as it comes and becoming a comet. Comets themselves are messengers from the early solar system, time capsules containing materials that have been frozen since before the planets formed. As they approach the sun, these dirty snowballs begin to warm, and their ices start to evaporate, creating the beautiful tails that stream out behind them. The tail always points away from the sun, pushed by solar wind and radiation pressure. Ancient peoples saw comets as omens, not understanding their true nature. But we now know they are simply visitors from the outer darkness, following their elliptical paths through the inner solar system before heading back out into the cold. The sun itself, which seems so constant and unchanging from Earth, is actually a seething ball of nuclear reactions, converting millions of tons of matter into energy every second. The energy produced in the core takes thousands of years to work its way to the surface, bouncing from atom to atom in a random walk through the dense interior. By the time that energy reaches the surface and flies off into space as light, the atoms that created it are long since transformed into something else. Light that warms your face left the sun's surface about 8 minutes ago, but was created in the core long before humans walked the Earth. Solar flares burst from the sun's surface, releasing enormous amounts of energy in minutes. These eruptions can send billions of tons of solar material hurtling into space at millions of miles per hour. When this material reaches Earth, it can create beautiful auroras as it interacts with our magnetic field, but it can also disrupt satellites and power grids. The sun's activity follows an 11-year cycle, waxing and waning in a rhythm that we can predict but don't fully understand. During solar maximum, flares and sunspots become common, while during solar minimum, the sun's face is relatively smooth and quiet. The Earth's magnetic field, which protects us from harmful solar radiation, is not fixed in place. It wanders slowly, and geological evidence shows that it has flipped many times throughout history, with north becoming south and south becoming north. The process takes thousands of years, and during the transition, the field becomes weak and complicated, with multiple north and south poles appearing in different locations. We can see the record of these flips in ancient rocks, which preserve the direction of the magnetic field at the time they formed. The field appears to be weakening now, though whether this heralds a coming flip or is merely a temporary fluctuation, we cannot yet say. Asteroids drift through space, remnants of a planet that never formed in the gap between Mars and Jupiter. Most orbit peacefully in the asteroid belt, but some have been nudged onto paths that bring them closer to the sun, occasionally crossing Earth's orbit. Impacts from these space rocks have shaped Earth's history, carving craters and, in at least one case, causing a mass extinction. Yet they also may have brought the building blocks of life to our planet, delivering water and organic compounds in the early days of the solar system. We now track these near-Earth objects carefully, mapping their orbits and assessing any potential danger. Meteorites that fall to Earth offer us samples of the solar system delivered free of charge. These rocks come in many varieties, some made of metal, others of stone, and some a mixture of both. The most primitive meteorites, called carbonaceous chondrites, contain tiny round inclusions called chondrules, which may be among the first solid objects that formed in the solar nebula. By studying these ancient stones, we can learn about conditions in the early solar system, reading the chemical signatures left behind from those formative times. The stars we see at night are not fixed in their positions, but are moving through space at considerable speeds. Over human lifetimes, these movements are too small to notice, but over thousands of years, the constellations slowly change shape as the stars drift in different directions. Each star follows its own path through the galaxy, orbiting the galactic center over hundreds of millions of years. Our Sun, along with its family of planets, is currently passing through a relatively empty region of space, moving at about 450,000 miles per hour relative to the center of the Milky Way. Binary star systems where two stars orbit each other are actually more common than single stars like our Sun. These stellar pairs slowly circle their common center of mass, sometimes taking days to complete an orbit, sometimes taking years or even centuries. From a planet orbiting such a system, you might see two suns in the sky, rising and setting in a complex pattern. Some binary systems are so close, the material flows from one star to the other, creating spectacular displays of cosmic exchange. Others are so distant that each star appears alone to any potential observers on worlds circling them. Red dwarf stars, smaller and cooler than our Sun, are the most common type of star in the galaxy. They burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. Some of these tiny stars have planets orbiting them, worlds that huddle close to their dim parent star to gather enough warmth. These planets might be locked in place, with one side always facing the star and the other in eternal darkness, creating a band of twilight around the edge where conditions might allow for liquid water. Giant stars, at the other end of the scale, burn bright and die young. These massive suns live fast, consuming their nuclear fuel in mere millions of years, rather than the billions that smaller stars enjoy. When they run out of fuel, they do not fade quietly, but instead explode in supernovae, brilliant flashes that can briefly outshine entire galaxies. In those final moments, the intense heat and pressure create new elements, forging heavy atoms that never existed before. These enriched materials are scattered into space, where they can eventually become part of new stars and planets. The remnants of supernovae expand outward in beautiful shells of glowing gas, creating nebulae that can persist for thousands of years. The Crab Nebula, for instance, is the remains of a supernova that was observed by astronomers in the year 1054. The expanding debris still glows today, energized by a rapidly spinning neutron star at its center. This pulsar, the collapsed core of the original star, spins 30 times every second, sweeping beams of radiation across the sky like a lighthouse. Each rotation takes only 30 milliseconds, a rate of spin almost impossible to imagine. Neutron stars are among the strangest objects in the universe, packing more mass than the Sun into a sphere only about 12 miles across. They are so dense that a teaspoon of neutron star material would weigh billions of tons. The gravity at the surface is so intense that it flattens anything that falls onto it to a thickness measured in atoms. Some neutron stars have magnetic fields trillions of times stronger than Earth's, creating magnetars that can release bursts of energy so powerful they affect instruments across the galaxy. Black holes, those regions of space where gravity becomes so strong that nothing can escape, form when the most massive stars collapse. At the heart of a black hole lies a singularity, a point where our understanding of physics breaks down. Surrounding this is the event horizon, the boundary beyond which not even light can return. Despite their name, black holes are not really holes at all, but incredibly dense objects. If you could see one directly, which you cannot, you would notice a dark sphere outlined by the bent and distorted light from stars behind it. Time itself behaves strangely near a black hole. The intense gravity slows time, so that a clock falling toward the event horizon would appear to tick slower and slower to a distant observer. From the perspective of something falling in, however, time would seem to pass normally, even as it crossed the point of no return. This difference in the flow of time is not an illusion, but a real effect of gravity's influence on space-time. The universe appears quite different depending on where you are and how fast you are moving. At the center of nearly every large galaxy, there appears to be a supermassive black hole, millions or billions of times the mass of the Sun. These galactic monsters sit quietly for the most part, but when gas falls toward them, it heats up and glows brilliantly before disappearing beyond the event horizon. The disk of inflowing material can outshine all the stars in the galaxy combined, creating what astronomers call an active galactic nucleus. Jets of material can be launched from near the black hole, shooting out perpendicular to the disk at close to the speed of light. Galaxies themselves come in many shapes and sizes. Spiral galaxies like our Milky Way have graceful arms that sweep out from a central bulge, while elliptical galaxies are smooth and round, having used up most of their gas and formed most of their stars long ago. Irregular galaxies have no particular shape, their structure disrupted by interactions with neighbors or by their own chaotic star formation. All of these galaxies formed from small fluctuations in the density of the early universe, regions that were slightly denser than average and gradually pulled in more matter. The Milky Way, our home galaxy, is a barred spiral containing somewhere between 2 and 400 billion stars. We orbit within one of its spiral arms, about halfway out from the center to the edge, taking about 230 million years to complete one orbit around the galactic core. From our vantage point, we see the disk of the galaxy edge on, creating that milky band of light across the night sky that gave the galaxy its name. On a dark night, far from city lights, you can see that band clearly, a reminder of the vast cosmic structure of which we are a part. The Andromeda Galaxy, our nearest large galactic neighbor, is visible to the naked eye as a faint smudge of light in the constellation Andromeda. It is slightly larger than the Milky Way and contains perhaps 1 trillion stars. Despite being over 2 million light years away, it is approaching us at about 250,000 miles per hour. In about 4 billion years, Andromeda and the Milky Way will begin to merge, their stars passing by each other like interweaving mist. Despite the enormous numbers of stars involved, actual collisions between stars will be rare due to the vast distances between them. Globular clusters orbit in the outer regions of galaxies, spherical collections of hundreds of thousands or even millions of old stars. These clusters formed early in the universe's history, and their stars are among the oldest we can observe. Because they all formed together from the same cloud of gas, the stars in a globular cluster are all about the same age and have similar compositions. Studying these stellar populations helps us understand the early history of galaxies and the conditions that existed when the universe was young. Open clusters, by contrast, are looser groupings of younger stars that formed together more recently. The Pleiades, or Seven Sisters, is a well-known example visible in the night sky. These clusters gradually disperse over time as their stars drift apart, pulled by gravitational interactions with other objects in the galaxy. Eventually, the stars that once formed together become scattered throughout the galaxy, indistinguishable from the general stellar population. Only their similar ages and compositions hint at their shared origin. Between the stars lies the interstellar medium, a thin soup of gas and dust that fills the space in galaxies. Though extremely tenuous by Earth standards, this material is not uniformly distributed, but collects in clouds of varying density. The densest regions can collapse under their own gravity to form new stars, while other areas are swept clean by stellar winds and supernovae. Light passing through these dusty regions gets scattered and absorbed, sometimes creating dark patches in otherwise bright regions of the sky. Cosmic rays stream through space, particles accelerated to nearly the speed of light by violent cosmic events. These particles, mostly protons and atomic nuclei, rain down constantly on Earth's atmosphere, where they collide with air molecules and create cascades of secondary particles. Most cosmic rays come from supernova remnants in our galaxy, though the most energetic ones may originate from outside the Milky Way. Despite traveling vast distances, they carry information about the powerful processes that created them. Gamma-ray bursts, the most luminous events in the universe, can release in a few seconds more energy than the sun will emit in its entire lifetime. These intense flashes of gamma radiation come from the most distant reaches of the observable universe, so far away that we are seeing them as they were billions of years ago. They appear to be associated with the formation of black holes, either from the collapse of a massive star or from the merger of two neutron stars. For a brief moment, a gamma-ray burst can be brighter than all the other objects in the universe combined. Gravitational waves, ripples in the fabric of space-time itself, were predicted by Einstein over a century ago, but only detected directly in recent years. These waves are created by the most violent events in the universe, such as the merger of black holes or neutron stars. They travel at the speed of light, stretching and squeezing space as they pass. The waves that we have detected have traveled for billions of years across the universe, carrying information about events that happened long ago in distant galaxies. Dark energy, even more mysterious than dark matter, appears to be causing the expansion of the universe to accelerate. Discovered only in the late 1990s, this enigmatic force seems to be built into the very fabric of space itself. As space expands, more dark energy comes into existence, pushing galaxies apart at an ever-increasing rate. If this continues, the universe will grow increasingly empty and dark, with distant galaxies eventually receding so fast that their light can no longer reach us. The cosmic microwave background radiation, the afterglow of the Big Bang, fills all of space. This faint glow, invisible to the human eye, comes to us from every direction, a relic of the hot, dense state that existed when the universe was only 380,000 years old. By studying tiny variations in this radiation, scientists can learn about the structure of the early universe and test theories about cosmic evolution. These patterns, imprinted long ago, have been stretched and enlarged by cosmic expansion, but remain visible to our instruments. The universe itself is thought to have begun in the Big Bang, an event that marked not only the beginning of matter and energy, but also of space and time themselves. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, growing from smaller than an atom to larger than a galaxy in an incomprehensibly brief interval. This rapid expansion smoothed out any irregularities and set the initial conditions for everything that would follow. In the early universe, there were no stars, no galaxies, only a hot, dense plasma of particles and radiation. As the universe expanded and cooled, the first atomic nuclei formed, mostly hydrogen and helium with traces of lithium. But it would take hundreds of thousands of years before the universe cooled enough for electrons to combine with these nuclei to form neutral atoms. That moment, called recombination, is when the cosmic microwave background was released and the universe became transparent to light for the first time. First stars, forming from clouds of pristine hydrogen and helium, were likely much more massive than stars forming today. With no heavier elements to help them cool and contract, these stellar behemoths burned brilliantly but briefly, living only a few million years before exploding. Their deaths scattered the first heavy elements into space, enriching the gas from which later generations of stars would form. Every element in your body heavier than helium was created inside a star or in a supernova explosion. Exoplanets, planets orbiting stars other than the Sun, have been discovered in their thousands in recent decades. These worlds come in varieties we never imagined, from hot Jupiters orbiting close to their stars to super-Earths larger than our planet but smaller than Neptune. Some orbit in the habitable zones of their stars, where temperatures could allow liquid water to exist on their surfaces. Each discovery adds to our understanding of how planetary systems form and evolve, showing that our solar system is just one example among countless others. The search for life beyond Earth continues, focusing on places where liquid water might exist. In our solar system, this includes not only Mars, but also the moons, Europa and Enceladus, both thought to harbor subsurface oceans. Beyond our solar system, astronomers are beginning to analyze the atmospheres of exoplanets, looking for chemical signs that might indicate biological activity. The discovery of life elsewhere would be one of the most profound findings in human history, changing our understanding of our place in the universe. The molecules that form the basis of life on Earth, amino acids and nucleotides, have been found in meteorites and detected in interstellar clouds. This suggests that the building blocks of life are common throughout the universe, formed by ordinary chemical processes wherever the right conditions exist. Whether these molecules can assemble themselves into living systems and how often this happens remains unknown. But the universe appears to be a fertile place, full of the raw materials needed for life to emerge. SETI, the search for extraterrestrial intelligence, listens for signals from other civilizations that might exist among the stars. Radio telescopes scan the sky, looking for patterns that could not be produced by natural processes. So far, no confirmed signals have been detected, but the search continues. The universe is vast, and even if intelligent life is common, the distances between stars are so great that communication would be slow, messages taking years or centuries to cross the interstellar void. The Fermi paradox asks a simple question with profound implications. If intelligent life is common, where is everyone? Given the age and size of the galaxy, even civilizations that expand slowly should have colonized it by now, yet we see no evidence of anyone else. Perhaps life is rarer than we think, or perhaps intelligent life tends to destroy itself. Or maybe advanced civilizations have no interest in colonizing the galaxy. The silence of the cosmos remains one of the great unsolved mysteries. Voyager 1, launched in 1977, has now left the solar system and entered interstellar space, becoming the first human-made object to do so. It continues to travel outward, though it will take thousands of years to travel even a single light-year at its current speed. Aboard Voyager is a golden record containing sounds and images from Earth, a message to any future finder about the civilization that built it. Whether anyone will ever find it is unknowable, but it represents humanity's first physical message to the cosmos. The speed of light, about 86,000 miles per second, is not just the speed at which light travels, but appears to be a fundamental limit of the universe. Nothing with mass can reach this speed, and even light itself can be slowed when passing through matter. This cosmic speed limit means that the universe is filled with regions we can never visit, separated from us by distances too vast to cross in any reasonable time. The farther we look into space, the farther we look back in time, seeing distant galaxies not as they are now, but as they were billions of years ago. Space itself is expanding, carrying galaxies along with it. This is not motion through space, but the expansion of space itself, creating more distance between objects as time passes. Galaxies that are sufficiently far away are receding from us faster than the speed of light, not because they are moving that fast through space, but because the space between us is expanding at that rate. This means there is a cosmic horizon beyond which we cannot see, a boundary that grows more distant with time, but always remains. Wormholes, hypothetical tunnels through space-time, could potentially connect distant regions of the universe or even different points in time. Allowed by Einstein's equations, they would require exotic matter with negative energy density to keep them open. Whether such matter exists, or whether wormholes could form naturally or be created artificially, remains unknown. They exist in mathematics and imagination, tantalizing possibilities at the edges of our understanding of physics. Time dilation, the slowing of time in strong gravitational fields or at high speeds, is a real and measured effect. Astronauts on the International Space Station age slightly slower than people on Earth, though the difference is only milliseconds over the course of a mission. For someone falling into a black hole, time would appear to run normally, but to a distant observer, they would seem to slow down and freeze at the event horizon, their image gradually fading from view as the light from them becomes redder and redder. Quantum mechanics, the physics of the very small, reveals a universe that is fundamentally uncertain. Particles can be in multiple places at once, existing in a state of probability until measured. Pairs of particles can be entangled, linked in such a way that measuring one instantly affects the other, no matter how far apart they are. This strange behavior, well tested and confirmed by countless experiments, suggests that reality at its most basic level is far stranger than our everyday experience would suggest. The uncertainty principle states that there are fundamental limits to what we can know about certain pairs of properties. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our measuring instruments, but a fundamental property of nature. Virtual particles constantly pop into and out of existence in the vacuum of space, borrowing energy from nothing and paying it back so quickly that the debt goes unnoticed. These quantum fluctuations are not just theoretical, but have measurable effects. They create a small force between metal plates placed very close together, pushing them toward each other. Even in the emptiest reaches of space, this quantum foam churns constantly, a reminder that the vacuum is not truly empty. Hawking radiation, predicted but never observed, suggests that black holes are not entirely black. Quantum effects near the event horizon can create pairs of particles, with one falling into the black hole and the other escaping. From a distance, it appears as though the black hole is emitting radiation. Over incomprehensibly long periods of time, this process could cause black holes to evaporate completely, though the timescales involved are so vast that no black hole that exists today will evaporate for countless ages. The multiverse, a speculative but increasingly discussed idea, suggests that our universe may be just one of many. These other universes could have different physical laws, different constants of nature, or different dimensions. We might never be able to observe them directly, as they could be fundamentally disconnected from our own. Yet the mathematics of certain theories, such as eternal inflation, seem to predict their existence, raising profound questions about the nature of reality and our place within it. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. Different vibrational patterns of these strings give rise to different particles, much as different vibrations of a guitar string produce different notes. The theory requires additional dimensions beyond the three of space and one of time that we experience, dimensions that are curled up so small that we cannot perceive them. Whether string theory describes reality remains an open question, as it has proven difficult to test experimentally. The fine-tuning problem notes that many physical constants appear to be precisely calibrated to allow complex structures like atoms, stars, and life to exist. If the strength of gravity was slightly different, or if the charge of the electron was slightly altered, the universe would be a very different place, likely unable to support life as we know it. Some see this as evidence for design, others as a selection effect in a multiverse, and still others as an unexplained coincidence that may be resolved by future theories. Entropy, the measure of disorder in a system, tends to increase over time. This is why ice melts, why stirred coffee doesn't unstir, and why broken eggs don't reassemble. In the long term, this principle suggests that the universe is gradually running down, approaching a state of maximum entropy called heat death. In this far future state, all stars will have burned out, all black holes will have evaporated, and the universe will be filled with a thin, uniform soup of particles at near absolute zero. The arrow of time, the distinction between past and future, is closely tied to the increase of entropy. In the early universe, entropy was very low, representing a highly ordered state. As the universe has evolved, entropy has increased, and this increase is what gives time its direction. The fundamental laws of physics are largely time-symmetric, working the same forwards and backwards, yet our experience of time is clearly directional. This asymmetry remains one of the deepest mysteries in physics. Boltzmann brains, a thought experiment arising from considerations of thermodynamics and infinity, suggests that in an eternally existing universe, random fluctuations could occasionally produce conscious observers fully formed, complete with false memories. If the universe lasts forever, such occurrences, though incredibly rare, would eventually happen, and indeed happen infinitely many times. This leads to the uncomfortable conclusion that it might be more likely that you are such a fluctuation than a real person. The paradox highlights the strange implications of infinite time and random chance. The simulation hypothesis proposes that our reality might be an artificial simulation created by an advanced civilization. If it is possible to create detailed simulations of conscious beings, and if civilizations typically create many such simulations, then it becomes statistically likely that we exist within a simulation rather than in base reality. While unfalsifiable and perhaps unprovable, the idea raises interesting questions about the nature of existence and what it means to be real. Consciousness itself remains unexplained by science, the hard problem of how subjective experience arises from physical processes. We can map brain activity and understand neural mechanisms, but we cannot explain why there is something it is like to be you, to experience the redness of red or the feeling of pain. Some suggest consciousness is fundamental to the universe, others that it is an emergent property of complex systems, and still others that it is an illusion, though what experiences that illusion remains unclear. The overview effect, experienced by astronauts viewing Earth from space, is a cognitive shift in awareness reported by many who have seen our planet from orbit. The thin blue line of atmosphere, The absence of visible borders, the fragility and unity of the biosphere all become apparent from that vantage point. This perspective, showing Earth as a single interconnected system floating in the vastness of space, has been described as transformative, creating a deep sense of connection to the planet and all life upon it. The Great Filter is a proposed explanation for the Fermi paradox, suggesting that at some point between pre-life and an advanced civilization capable of colonizing the galaxy, there is a barrier that is extremely difficult to surpass. The question is whether this filter is behind us, meaning we have already passed the most difficult step, or ahead of us, meaning that civilizations typically destroy themselves or hit some other obstacle before achieving their full potential. The answer has implications for the long-term future of humanity. Megastructures, theoretical constructs that advanced civilizations might build, include Dyson spheres that would surround a star to capture all its energy, or ring worlds, vast rotating habitats that could provide the living area of millions of Earths. These constructs, while possible in principle, would require resources and engineering capabilities far beyond our current abilities. If such structures exist, we might detect them by their infrared signatures or by their unusual dimming patterns as they pass in front of distant stars. Fast radio bursts, brief pulses of radio waves from distant galaxies, last only milliseconds, but release as much energy as the Sun emits in several days. Their origin remains unclear, though they appear to come from billions of light-years away. Theories to explain them range from rotating neutron stars with extreme magnetic fields to more exotic possibilities. Each detection adds to the puzzle, slowly narrowing down the possibilities. Tidal locking occurs when the rotation of a body matches its orbital period, causing the same face to always point toward what it orbits. The Moon is tidally locked to Earth, which is why we always see the same side. Many exoplanets are thought to be tidally locked to their stars, creating one permanent day side and one permanent night side. On such worlds, weather patterns and climate would be dramatically different from Earth, with potentially constant winds flowing from the hot side to the cold side. Rogue planets drift through interstellar space unbound to any star. These worlds were either ejected from their original solar systems by gravitational interactions or formed in isolation. Without a sun to warm them, rogue planets would be cold, dark places, though some might retain heat from radioactive decay in their cores or from tidal heating if they have large moons. Life on such a world would face unique challenges, requiring energy sources other than sunlight. Water is surprisingly common in the universe, found in comets, on moons, and in the atmospheres of exoplanets. On Earth, water is essential for life, serving as a solvent for biochemistry and a medium for molecular interactions. Whether life based on different solvents could exist is unknown, but water's unique properties make it an excellent choice for biochemistry. The search for habitable worlds often focuses on finding liquid water, using it as a proxy for habitability. Extremophiles on Earth, organisms that thrive in conditions once thought to be uninhabitable, have expanded our understanding of where life might exist. Bacteria live in boiling hot springs, in acidic environments, in the extreme cold of Antarctica, and miles beneath the surface in solid rock. These discoveries suggest that life is resilient and adaptable, capable of surviving in a range of conditions. If life can exist in such extreme environments on Earth, perhaps it can exist in the harsh conditions found elsewhere in the solar system or beyond. Panspermia, the idea that life can spread from world to world via meteorites or other means, suggests that life on Earth may have originated elsewhere. Microbes can survive the radiation and cold of space for extended periods, and impacts can eject rocks from planets at velocities sufficient to escape their gravity. These rocks can then travel through space for millions of years before falling onto another world. If panspermia is correct, then life in the solar system or even the galaxy might share a common origin. The habitable zone around a star, sometimes called the Goldilocks zone, is the range of distances where a planet could maintain liquid water on its surface. Too close, and water boils away; too far, and it freezes solid. The width and location of this zone depends on the star's temperature and brightness. Red dwarfs have narrow habitable zones close to the star, while larger, hotter stars have wider zones farther out. Finding planets in the habitable zones of other stars is a key goal in the search for life beyond Earth. Technosignatures, the technological equivalent of biosignatures, are signs that an intelligent civilization might leave behind. These could include radio signals, optical pulses, atmospheric pollution from industrial activity, or the heat signatures of megastructures. While we have not detected any confirmed technosignatures, the search continues. As our instruments improve and we examine more stars, the chances of finding evidence of technology elsewhere in the universe increase. The Drake equation attempts to estimate the number of active, communicative civilizations in the galaxy by multiplying together factors such as the rate of star formation, the fraction of stars with planets, the number of planets that could support life per star, and so on. The problem is that most of these factors are highly uncertain, with estimates varying by orders of magnitude. The equation is less a tool for calculation than a framework for thinking about the question of extraterrestrial intelligence. Light pollution on Earth has grown to the point where most people living in cities never see a truly dark sky filled with stars. The Milky Way, once a common sight, is now invisible to a large fraction of humanity. This represents a loss of connection to the universe beyond our planet, a severing of a relationship that has existed for all of human history. Efforts to reduce light pollution aim not only to save energy and protect wildlife, but also to restore the night sky as a source of wonder and inspiration. The pale blue dot, a photograph of Earth taken by Voyager 1 from a distance of about 4 billion miles, shows our planet as a tiny speck of light suspended in a sunbeam. Astronomer Carl Sagan reflected on this image, noting how it underscores the fragility and insignificance of our world in cosmic terms, while simultaneously highlighting its value as the only home we have ever known. Every person who has ever lived has done so on that pale blue dot, and it remains our only refuge in a vast and uncaring universe. The observable universe has a radius of about 46 billion light-years, a distance greater than the age of the universe multiplied by the speed of light due to the expansion of space. Beyond this horizon, galaxies are receding so quickly that their light will never reach us. This means there are parts of the universe we can never observe, regions forever beyond our reach. The observable universe represents only a portion of the total universe, which may be infinite. The cosmic web, the large-scale structure of the universe, shows galaxies arranged in filaments and sheets surrounding vast voids. This pattern emerged from the small density fluctuations in the early universe, amplified by gravity over billions of years. Dark matter provides the scaffolding for this structure, with ordinary matter falling into the gravitational wells it creates. Mapping this cosmic web helps us understand the distribution of matter in the universe and test our models of cosmic evolution. Great walls, enormous structures stretching across hundreds of millions of light-years, are the largest known structures in the universe. The Sloan Great Wall, the Hercules, Corona Borealis Great Wall, and others represent concentrations of galaxies on scales that challenge our understanding of structure formation. These immense features took billions of years to assemble and contain the mass of quadrillions of suns. They remind us that even galaxies and clusters are just small components of something much larger. Voids, the vast empty regions between filaments in the cosmic web, contain very few galaxies. These underdense areas can be hundreds of millions of light-years across, representing some of the largest coherent structures in the universe. Despite their emptiness, they are not completely devoid of matter, containing occasional isolated galaxies and thin wisps of gas. The expansion of the universe affects voids differently than dense regions, causing them to expand faster and become even emptier over time. Quasars, among the brightest objects in the universe, are powered by supermassive black holes actively consuming matter. The material falling toward the black hole forms an accretion disk that heats to millions of degrees, emitting enormous amounts of light. Jets of particles can be launched perpendicular to the disk, extending for thousands of light-years into space. Quasars were much more common in the early universe, when galaxies were smaller and more gas-rich, providing ample fuel for their central black holes. When material in the jet emits a burst of energy aimed in our direction, we see a corresponding increase in the blazer's brightness. These variations can occur over days or even hours, providing insights into the small-scale physics of jets and accretion disks. Blazars are among the most variable objects in the sky and important sources of high-energy particles. The Hubble constant, which describes how fast the universe is expanding, has been measured by different methods with slightly different results. This discrepancy, known as the Hubble tension, suggests either that our measurements have unknown errors or that our understanding of cosmic expansion is incomplete. Resolving this tension is one of the major challenges in modern cosmology, as it touches on fundamental questions about dark energy, the early universe, and the ultimate fate of the cosmos. Cosmic inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang, was proposed to explain certain features of the universe, such as its large-scale uniformity and the flatness of space. Inflation stretched quantum fluctuations to macroscopic scales, creating the seeds that would eventually grow into galaxies and galaxy clusters. While inflation is supported by several lines of evidence, including patterns in the cosmic microwave background, direct proof remains elusive. Primordial black holes, if they exist, would have formed in the very early universe from density fluctuations shortly after the Big Bang. Unlike black holes that form from stars, primordial black holes could have a wide range of masses, from much less than a gram to thousands of solar masses. Some researchers have suggested that primordial black holes could account for some or all of dark matter, though this remains speculative. Detecting them directly would provide a unique window into conditions in the first moments of cosmic history. The cosmological principle states that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same in all directions and at all locations. This assumption underlies most of our models of the universe and appears to be well supported by observations. However, some anomalies in the cosmic microwave background and the distribution of galaxies hint at possible violations of this principle. Whether these are statistical flukes or signs of new physics remains an open question. Baryon asymmetry, the fact that the universe contains more matter than antimatter, is one of the great unsolved problems in physics. In the early universe, matter and antimatter should have been created in equal amounts, and they should have annihilated each other, leaving only energy. Yet a small excess of matter survived, about 1 part in a billion, and this excess is what makes up everything we see. Why this asymmetry exists, and what processes in the early universe created it, remains unknown. Antimatter, the mirror image of ordinary matter, has been created and studied in laboratories. Antiparticles have the same mass as their corresponding particles, but opposite charge. When matter and antimatter meet, they annihilate, converting their mass entirely into energy. This process releases far more energy per kilogram than any chemical or nuclear reaction, making antimatter a staple of science fiction propulsion systems. In reality, producing and storing antimatter is extraordinarily difficult and expensive. Neutrinos, nearly massless particles that interact very weakly with matter, stream through the universe in vast numbers. Trillions pass through your body every second without you noticing. They are produced in nuclear reactions in the sun, in supernovae, and in radioactive decay. Despite their abundance, neutrinos are difficult to detect, requiring large underground detectors filled with thousands of tons of water or ice. Studying neutrinos helps us understand nuclear processes in the sun, supernova explosions, and the fundamental properties of matter. The Big Rip is a hypothetical end to the universe in which dark energy increases over time, eventually becoming so strong that it tears apart galaxies, stars, planets, and ultimately atoms themselves. This scenario depends on the properties of dark energy, which remain poorly understood. If dark energy is truly a cosmological constant, the universe will expand forever, growing cold and dark, but never experiencing a big rip. If dark energy strengthens over time, the universe could end in this catastrophic disintegration. The Big Crunch, an alternative fate for the universe, would occur if the expansion of the universe eventually reverses and everything begins to fall back together. Galaxies would collide and merge, stars would crowd closer, and eventually all matter would collapse into a singularity similar to the Big Bang, but running in reverse. Whether this can happen depends on the amount and properties of dark energy. Current observations suggest that the universe will not recollapse, but our understanding of dark energy remains incomplete. Heat death, the most likely fate of the universe based on current evidence, is a state of maximum entropy, where no more energy can be extracted to do work. Stars will cease to shine, black holes will evaporate, and matter itself may decay into radiation. The universe will approach a uniform temperature just above absolute zero, a cold, dark, and empty place where nothing happens and nothing changes. This fate awaits us in the incomprehensibly distant future, trillions upon trillions of years from now. The anthropic principle notes that the universe must be compatible with the existence of observers, otherwise there would be no one to observe it. The strong version of the principle suggests that the universe is somehow required to allow for consciousness, while the weak version simply states that we should not be surprised to find ourselves in a universe capable of supporting life, as we could not exist in a universe that was not. The principle is controversial, as some see it as tautological, while others see it as a profound insight. This question, perhaps the most fundamental of all, lies at the boundary between physics and philosophy. Physics can describe how the universe evolved from the Big Bang, but it cannot explain why the Big Bang occurred or why the laws of physics take the form they do. Some suggest that the universe is self-creating, arising from a quantum fluctuation, while others invoke a multiverse where all possibilities are realized. The concept of time's beginning remains one of the deepest puzzles we face. Before the Big Bang, the very notion of before may be meaningless, as time itself may have begun with the universe. Others propose that time is cyclical, with universes being born, evolving, and dying, only to be reborn again in an endless cycle. The nature of time, so familiar in our everyday experience, becomes strange and slippery when we examine it at cosmic scales. Cosmic voids appear to expand faster than the average expansion rate of the universe, creating ever larger empty regions. This may be because voids contain less matter to slow the expansion through gravitational attraction. As time passes, the cosmic web becomes more pronounced, with denser filaments and emptier voids. This increasing contrast shapes how galaxies evolve and interact, influencing star formation and the development of structure throughout the universe. The Botas void, discovered in 1981, is one of the largest known voids in the universe. It contains very few galaxies across a region hundreds of millions of light-years in diameter. Early observers called it the Great Nothing, puzzled by how such a vast region could contain so little. We now understand voids as natural features of cosmic structure, but their sheer scale still impresses. Standing within such a void, if that were possible, you would see galaxies only in the most distant reaches of the sky, with vast emptiness all around. Gravitational lensing occurs when light from distant objects passes near massive foreground objects, causing the path of light to bend. Sometimes the lensing creates multiple images of the same distant galaxy, or stretches it into arcs and rings. These cosmic mirages also allow us to map the distribution of dark matter, as the amount of lensing reveals where mass is concentrated. Einstein rings, perfect circles of light created when a distant galaxy sits directly behind a massive foreground object, are rare and beautiful examples of gravitational lensing. The light from the background galaxy is bent around the foreground mass, creating a ring of light. These formations serve as natural telescopes, magnifying distant objects and allowing us to study galaxies that would otherwise be too faint to observe. The precision of the ring depends on the alignment between source, lens, and observer. Microlensing occurs when a smaller object, even a single star or planet, passes in front of a more distant star. The foreground object's gravity focuses the background star's light, causing a temporary brightening that can last hours to weeks. This technique has been used to discover exoplanets and to search for dark matter in the form of compact objects. Each microlensing event is unique, never to be repeated, as the alignment that created it continues to shift. The concept of a parallel universe proposes that there might be other universes existing alongside our own, perhaps with different physical laws or even different numbers of dimensions. These universes would be forever beyond our reach, impossible to observe or interact with. The idea emerges from certain interpretations of quantum mechanics and from some models of cosmic inflation. While purely speculative, parallel universes challenge our understanding of what we mean by the universe and reality itself. Vacuum decay, a theoretical possibility in physics, suggests that the vacuum of space might not be in its lowest energy state. If a lower energy state exists, the vacuum could undergo a phase transition, creating a bubble of true vacuum that would expand at the speed of light, fundamentally altering the laws of physics within it. This would destroy everything in its path, rewriting reality at the most basic level. Whether this can happen, and whether our universe is stable or merely metastable, remains unknown. The holographic principle suggests that all the information contained within a volume of space can be encoded on the boundary of that space, much like a hologram encodes three-dimensional information on a two-dimensional surface. This strange idea emerges from studies of black holes and quantum gravity. If true, it would mean that our three-dimensional reality might be a projection from information encoded on a two-dimensional surface. Black hole information paradox arises from the apparent conflict between quantum mechanics and general relativity. When matter falls into a black hole, its information appears to be lost forever, yet quantum mechanics says information cannot be destroyed. If black holes eventually evaporate via Hawking radiation, what happens to the information they contain? This paradox has led to deep investigations into the nature of space, time, and information itself. Proposed solutions range from information being encoded in Hawking radiation to the event horizon being a more complex structure than previously thought. Firewall paradox suggests that the event horizon of a black hole might not be the smooth, crossable boundary that general relativity predicts, but instead a surface of high-energy particles that would incinerate anything trying to pass through. This idea attempts to resolve the information paradox, but creates its own problems, as it seems to violate the equivalence principle, a cornerstone of general relativity. The debate over black hole firewalls remains active, touching on fundamental questions about how quantum mechanics and gravity interact. White holes, theoretical time, reversed versions of black holes, would eject matter and energy rather than consuming it. Nothing could enter a white hole, just as nothing can escape a black hole. While mathematically consistent with general relativity, white holes are thought to be unstable and would quickly transform into black holes. No white holes have been observed, and it remains unclear whether they could exist in reality or are merely mathematical curiosities. Cosmic strings, if they exist, would be extremely thin, dense defects in space-time left over from the early universe. These one-dimensional structures would be thinner than an atom, but could stretch across cosmic distances with enormous mass. They would warp space-time around them in distinctive ways, creating double images of objects behind them. While predicted by some theories of the early universe, cosmic strings have never been detected. Their existence would have profound implications for our understanding of phase transitions in the early cosmos. Domain walls, another type of cosmic defect, would be two-dimensional structures separating regions of space where some field has different values. Like cosmic strings, they are predicted by certain theories but have not been observed. If they existed in large numbers, they would have affected the evolution of the universe in ways we do not see, suggesting either that they never formed or that they decayed early in cosmic history. Monopoles, hypothetical particles with only one magnetic pole, north or south, are predicted by many theories of particle physics. In everyday experience, magnets always have both poles, and cutting a magnet in half creates two smaller magnets, each with both poles. But at high energies, conditions that existed in the early universe, monopoles might have formed. The fact that we do not see monopoles today is part of what motivated the theory of cosmic inflation, which would have diluted their density to undetectable levels. Tachyons, particles that travel faster than light, are allowed by special relativity under certain mathematical conditions, though they would have imaginary mass and strange causal properties. If tachyons exist, they would experience time backwards, seeing effects before causes. No tachyons have been detected, and most physicists believe they are purely theoretical, perhaps indicating an instability in a theory rather than actual particles. Their existence would require a radical rethinking of causality and the nature of time. The vacuum catastrophe refers to the enormous disagreement between the theoretical prediction for the energy density of empty space and the observed value. Quantum field theory predicts a vacuum energy about 120 orders of magnitude larger than what we observe. This is perhaps the worst prediction in the history of physics. Quantum entanglement, sometimes called spooky action at a distance, links particles in ways that seem to defy our intuitions about locality. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. This does not allow faster-than-light communication, as the results appear random to each observer, but it does create correlations that cannot be explained by classical physics. Entanglement is well verified experimentally and lies at the heart of emerging technologies like quantum computers and quantum cryptography. The measurement problem in quantum mechanics asks what happens when a quantum system is measured. Before measurement, a particle exists in a superposition of states, but measurement seems to collapse this superposition into a definite outcome. What causes this collapse? Is it consciousness, interaction with a macroscopic measuring device, or something else? Different interpretations of quantum mechanics provide different answers, but the problem remains unresolved after nearly a century of debate. The many worlds interpretation suggests that measurement does not collapse the wave function, but instead splits reality into multiple branches, one for each possible outcome. In this view, all possibilities are realized, just in different worlds. When you measure a particle's spin, the universe branches into one world where the result is up and another where it is down. Both versions of you exist, each unaware of the other. This interpretation is deterministic and avoids the measurement problem, but at the cost of an ever-multiplying number of worlds. The wave function describes probabilities, not an underlying reality. Measurement causes a genuine, discontinuous collapse of the wave function to a definite state. This interpretation treats measurement as a fundamental process, but does not explain what qualifies as a measurement or why collapse occurs. Despite its practical success, it leaves many questions unanswered. Pilot wave theory, also known as de Broglie-Bohm theory, proposes that particles have definite positions at all times, guided by a pilot wave described by the wave function. In this deterministic interpretation, there is no measurement problem, because particles always have definite properties. The appearance of randomness comes from our ignorance of initial conditions. While this interpretation makes the same predictions as standard quantum mechanics, it requires particles to be influenced by the pilot wave in a non-local way. Quantum tunneling allows particles to pass through barriers that they classically should not be able to surmount. A particle encountering an energy barrier has a small probability of appearing on the other side, as if it tunneled through. This effect is essential for many processes, including nuclear fusion in stars and the operation of electronic devices like tunnel diodes. Tunneling demonstrates the wave-like nature of particles and the probabilistic nature of quantum mechanics. Zero-point energy is the lowest possible energy that a quantum system can have. Even at absolute zero, quantum systems retain this minimum energy due to the uncertainty principle. Virtual particles constantly appear and disappear in the vacuum, borrowing and repaying energy on timescales too short to violate conservation laws. This quantum foam means that empty space is never truly empty, but seethes with activity at the smallest scales. The Casimir effect, a consequence of zero-point energy, creates a small attractive force between two uncharged metal plates placed very close together in a vacuum. The space between the plates restricts which virtual particles can exist there, creating a pressure difference that pushes the plates together. This effect has been measured experimentally and provides direct evidence for the reality of vacuum fluctuations. Quantum computing harnesses superposition and entanglement to process information in fundamentally new ways. While a classical bit is either 0 or 1, a quantum bit or qubit can be in a superposition of both states. Multiple qubits can be entangled, allowing quantum computers to explore many possibilities simultaneously. For certain problems, this provides exponential speedups over classical computers. Building large-scale quantum computers remains technically challenging, but progress continues steadily. Quantum cryptography uses the principles of quantum mechanics to create communication channels that are theoretically secure against any eavesdropping. Any attempt to intercept and measure quantum information disturbs it in a detectable way, alerting the legitimate parties to the presence of an eavesdropper. This security does not rely on computational complexity as classical cryptography does, but on the fundamental laws of physics. Quantum key distribution systems are already commercially available. Quantum teleportation transfers the quantum state of a particle to another particle at a distant location using entanglement and classical communication. The original particle is destroyed in the process, and the state appears at the destination. This is not teleportation of matter or energy, but of information. Despite its name, quantum teleportation cannot be used for faster-than-light communication, as it requires a classical channel that travels at or below light speed. Decoherence explains how quantum systems transition to classical behavior when they interact with their environment. A quantum superposition is fragile, easily disturbed by interactions with surrounding particles, light, and fields. These interactions effectively measure the quantum system, collapsing superpositions and creating definite states. Decoherence helps explain why we do not see quantum effects like superposition in everyday macroscopic objects. Isolating quantum systems from decoherence is one of the main challenges in building quantum computers. Schrödinger's cat, a famous thought experiment, illustrates the strangeness of quantum mechanics when applied to macroscopic objects. A cat in a box is simultaneously alive and dead, according to quantum mechanics, until someone opens the box and observes it. This paradox highlights the measurement problem and the unclear boundary between quantum and classical physics. While no one believes actual cats exist in superpositions, the thought experiment continues to provoke discussion about the interpretation of quantum mechanics. The EPR paradox, proposed by Einstein, Podolsky, and Rosen, argued that quantum mechanics must be incomplete because it allows entangled particles to influence each other instantaneously over arbitrary distances. Einstein called this spooky action at a distance and believed there must be hidden variables providing a more complete description. However, experiments testing Bell's inequalities have shown that nature really does exhibit these non-local correlations. Quantum mechanics appears to be correct, and the universe is stranger than Einstein hoped. Bell's theorem and the experiments it inspired demonstrated that no theory of local hidden variables can reproduce all the predictions of quantum mechanics. The correlations between entangled particles are stronger than any local realistic theory allows. This profound result shows that we must give up either locality, the idea that distant events cannot instantly affect each other, or realism, the idea that particles have definite properties independent of measurement. Most physicists have chosen to give up local realism, accepting that nature is fundamentally non-local. The double-slit experiment demonstrates wave-particle duality, showing that particles like electrons can behave as waves. When electrons pass through two slits, they create an interference pattern on a screen beyond, just as waves do. But when we try to determine which slit each electron passes through, the interference pattern disappears, and the electrons behave like particles. The act of observation changes the outcome. This experiment, simple in concept but profound in implication, captures the essential mystery of quantum mechanics. Complementarity, a principle proposed by Niels Bohr, states that quantum objects have complementary properties that cannot be observed simultaneously. Position and momentum are complementary, as are wave and particle aspects. This is not a limitation of our measuring instruments, but a fundamental feature of reality. Complementarity suggests that quantum objects do not have a single, complete description, but must be understood through multiple, mutually exclusive perspectives. Quantum field theory extends quantum mechanics to fields, treating particles as excitations or quanta of underlying fields that fill all of space. Photons are quanta of the electromagnetic field, electrons are quanta of the electron field, and so on. This framework successfully describes the standard model of particle physics, explaining the electromagnetic, weak, and strong forces. Quantum field theory is one of the most successful theories in physics, making predictions of extraordinary precision. The standard model of particle physics describes the known elementary particles and three of the four fundamental forces: electromagnetism, the weak force, and the strong force. It has been tested extensively and confirmed to remarkable precision. Yet the standard model is known to be incomplete. It does not include gravity, does not explain dark matter, and leaves many parameters unexplained. Physicists search for a more complete theory, often called physics beyond the standard model. The Higgs boson, discovered at CERN in 2012, is associated with the Higgs field, which gives mass to other particles. Without the Higgs mechanism, particles like electrons and quarks would be massless, and the universe would be very different. The discovery of the Higgs boson confirmed a key prediction of the standard model and completed the inventory of its particles. Studying the Higgs in detail may reveal clues to physics beyond the standard model. Quarks, the building blocks of protons and neutrons, come in 6 flavors: up, down, strange, charm, bottom, and top. They are never found in isolation, but are always confined within composite particles called hadrons. The strong force that binds quarks together has the peculiar property that it grows stronger with distance, like a rubber band. Gluons, the carriers of the strong force, bind quarks together inside protons and neutrons. Unlike photons, which are electrically neutral, gluons carry color charge and can interact with each other. This self-interaction makes the strong force more complex than electromagnetism and leads to phenomena like confinement and asymptotic freedom, where quarks behave almost freely at very short distances, but are tightly bound at larger scales. Leptons are a family of particles that includes electrons, muons, and tau particles, along with their associated neutrinos. Unlike quarks, leptons do not experience the strong force. Each lepton has an antiparticle with opposite charge. The electron is stable, but muons and tau particles decay rapidly into lighter particles. Neutrinos, the lightest leptons, are electrically neutral and interact only weakly, making them extremely difficult to detect. The weak force is responsible for certain types of radioactive decay and plays a crucial role in nuclear processes. It is the only force that can change one type of quark into another, enabling processes like beta decay. The weak force is carried by W and Z bosons, which are massive particles, unlike the massless photon. This mass makes the weak force short-ranged, effective only over distances smaller than an atomic nucleus. Grand unified theories attempt to unify the electromagnetic, weak, and strong forces into a single force that would manifest at very high energies. At the energies available in particle accelerators, these forces appear distinct, but at the enormous energies that existed shortly after the Big Bang, they may have been unified. evidence for grand unification could come from proton decay, though experiments searching for this process have not yet found it. Supersymmetry proposes that every known particle has a supersymmetric partner differing by half a unit of spin. If supersymmetry exists, it could help explain the hierarchy problem, stabilize the Higgs mass, and provide candidates for dark matter. Despite extensive searches, no supersymmetric particles have been discovered. This does not rule out supersymmetry, as the partners might be too heavy for current accelerators to produce, but it does constrain the theory. Extra dimensions, beyond the three spatial dimensions we experience, are predicted by string theory and some other theories attempting to unify gravity with the other forces. These dimensions might be curled up at scales too small to detect, or we might be confined to a three-dimensional slice of a higher dimensional space. Experiments have searched for evidence of extra dimensions through their effects on gravity or particle physics, but none have been found so far. The hierarchy problem asks why gravity is so much weaker than the other forces. An electron and proton attract each other electrically with a force about 10 to the 40th power times stronger than their gravitational attraction. This enormous difference seems unnatural and may hint at new physics. Some theories address this by proposing extra dimensions or new symmetries. Solving the hierarchy problem could lead to a deeper understanding of the fundamental forces. Axions, hypothetical particles proposed to solve certain problems in particle physics, could also make up dark matter. These very light particles would have been produced in the early universe and might still fill space today. Experiments are searching for axions using sensitive detectors that look for their conversion into photons in strong magnetic fields. If discovered, axions would address multiple mysteries at once, a satisfying convergence that theorists find appealing. WIMPs, or weakly interacting massive particles, are another candidate for dark matter. These particles would interact only through the weak force and gravity, making them very difficult to detect. They could be produced in particle colliders or detected directly when they occasionally collide with atomic nuclei in underground detectors. Despite decades of searching, no conclusive detection of WIMPs has been made, though experiments continue with increasing sensitivity. MACOs, or massive compact halo objects, are ordinary matter objects like brown dwarfs, black holes, or neutron stars that could potentially account for dark matter. Unlike exotic particles, MACOs would be made of familiar matter, just in forms that emit little or no light. Microlensing surveys have searched for MACOs and found some, but not enough to explain all of dark matter. Most dark matter appears to be something more exotic. Modified gravity theories propose that dark matter might not exist at all. Instead, our understanding of gravity might be incomplete, with the law of gravity changing on large scales. Modified Newtonian dynamics, or MOND, successfully explains some galaxy rotation curves without dark matter, but it struggles with other observations like gravitational lensing. Most evidence still favors the existence of dark matter over modified gravity, but the debate continues. The cosmological constant problem is closely related to dark energy. Einstein introduced the cosmological constant to create a static universe, then called it his biggest blunder, when the universe was found to be expanding. Ironically, observations now suggest that dark energy, which acts very much like a cosmological constant, does exist. The problem is explaining why its value is what it is. Theory predicts it should be either zero or vastly larger than observed. Why it has the small, non-zero value we measure is a major mystery. Quintessence is a proposed form of dark energy that, unlike the cosmological constant, changes over time. The energy density of quintessence would evolve as the universe expands, potentially explaining why dark energy seems to dominate at this particular epoch. Different models of quintessence predict different futures for the universe. Distinguishing between a cosmological constant and quintessence requires precise measurements of how dark energy has changed over cosmic history. The coincidence problem asks why dark energy and matter have comparable densities today when they scale differently with cosmic expansion. In the past, matter dominated. In the future, dark energy will dominate completely. The fact that we live at the special time when they are roughly balanced seems like an unlikely coincidence. Some argue this is a selection effect, as intelligent observers might only arise during this brief window, but the problem remains philosophically troubling. Phantom energy is a hypothetical form of dark energy that becomes denser as the universe expands, opposite to how normal matter and even a cosmological constant behave. If phantom energy exists, it would lead to a big rip, where the expansion accelerates so much that galaxies, stars, planets, and eventually atoms are torn apart. Current observations do not rule out phantom energy, though they seem to favor a cosmological constant. The question remains open. Baryonic acoustic oscillations are regular, periodic fluctuations in the density of matter in the early universe, imprinted as the universe expanded and cooled. These patterns, fossilized in the current distribution of galaxies, serve as a cosmic ruler that helps measure the expansion history of the universe. By comparing the size of these patterns at different distances and times, astronomers can track how dark energy has affected cosmic expansion. The precision of these measurements continues to improve, constraining models of dark energy. The Lyman alpha forest consists of absorption lines in the spectra of distant quasars created by clouds of neutral hydrogen between us and the quasar. Each cloud absorbs light at a specific wavelength corresponding to the Lyman alpha transition of hydrogen, but cosmic expansion shifts this wavelength. The result is a forest of absorption lines at different wavelengths, mapping out the distribution of gas along our line of sight. Studying the Lyman alpha forest reveals information about the intergalactic medium and the large-scale structure of the universe. Quasar absorption systems allow us to study the chemical composition of gas clouds billions of light-years away. When light from a distant quasar passes through these clouds, atoms absorb specific wavelengths, leaving dark lines in the quasar's spectrum. By analyzing these absorption lines, we can determine what elements are present and in what quantities. This reveals how the universe has been enriched with heavy elements over time, as generations of stars have lived and died, scattering their fusion products into space. Reionization marks the period when the first stars and galaxies began producing enough ultraviolet light to ionize the neutral hydrogen that filled the universe. Before reionization, the universe was dark and filled with neutral gas. The light from early stars gradually ionized this gas, creating bubbles of ionized material that grew and eventually merged. By about 1 billion years after the Big Bang, reionization was complete, and the universe became largely transparent to ultraviolet light. Studying reionization helps us understand the first generations of stars and galaxies. Population 3 stars, the very first stars in the universe, formed from clouds of pristine hydrogen and helium with no heavier elements. Without metals to help them cool and fragment, these clouds likely formed much more massive stars than we see forming today. These giants would have burned bright and fast, living only a few million years before exploding as supernovae. Their explosions enriched the surrounding gas with the first heavy elements, enabling the formation of later generations of stars. No population 3 stars have been directly observed, as they all died long ago. The epoch of galaxy formation saw small proto-galaxies merging together over billions of years to form the large galaxies we see today. The Milky Way itself has grown through mergers and continues to cannibalize smaller satellite galaxies. Deep images of distant galaxies show them as they were billions of years ago, appearing smaller, more irregular, and more actively forming stars than nearby galaxies. By studying galaxies at different distances and thus different times, we can piece together how galaxies evolved over cosmic history. Starburst galaxies form stars at an extraordinarily rapid rate, sometimes hundreds of times faster than the Milky Way. These bursts often result from galaxy mergers, which compress gas and trigger intense star formation. A starburst phase is relatively brief, perhaps lasting only 100 million years, but during that time, a galaxy can convert a large fraction of its gas into stars. The intense radiation from young, massive stars can eventually blow away the remaining gas, quenching further star formation. Ultra-luminous infrared galaxies emit most of their light in the infrared, powered by either intense star formation or an active galactic nucleus, or both. The infrared emission comes from dust heated by starlight or by the energetic environment near a black hole. These galaxies are often dusty and obscured in visible light, making infrared observations essential. Many ultra-luminous infrared galaxies are undergoing mergers, with the collision triggering both star formation and black hole growth. Dark galaxies, hypothetical galaxies made mostly of dark matter with little or no stars, might exist, but would be extremely difficult to detect. Without stars, they would emit no light and could only be detected through their gravitational effects or by the hydrogen gas they contain. Some objects that might be dark galaxies have been tentatively identified, but confirming their nature remains challenging. If dark galaxies exist in large numbers, they could help explain the missing satellite problem, where simulations predict more small galaxies around large ones than we observe. Tidal streams, long arcs of stars stripped from satellite galaxies or globular clusters by the gravity of a larger galaxy, trace out the gravitational potential and dark matter distribution of the larger galaxy. The Sagittarius stream, for instance, wraps around the Milky Way, marking the path of a small galaxy being torn apart by our galaxy's gravity. By studying multiple tidal streams, astronomers can map the Milky Way's dark matter halo in detail. Stellar streams show that the Milky Way has consumed many smaller galaxies over its history. Each merger leaves behind debris in the form of stars scattered along orbital paths. These stellar streams are fossils of past interactions, preserving information about the masses and orbits of the merged galaxies. By identifying and studying these streams, we can reconstruct the merger history of the Milky Way and test models of how galaxies grow through hierarchical assembly. Hypervelocity stars are stars moving fast enough to escape the gravity of the Milky Way entirely. These stars likely gained their enormous speeds through close encounters with the supermassive black hole at the galaxy's center, which flung them outward at thousands of kilometers per second. Studying hypervelocity stars can reveal information about the black hole and the processes near it. Some may eventually leave the galaxy completely, wandering into intergalactic space. Runaway stars are stars ejected from their birthplaces at high speeds, though not fast enough to escape the galaxy. They can be produced when a companion star explodes as a supernova, releasing the remaining star from the binary orbit, or through dynamical interactions in dense star clusters. These stars plow through the interstellar medium, creating bow shocks, where they compress the gas ahead of them, visible in infrared images as arc-shaped structures. Rogue black holes, ejected from their host galaxies by gravitational interactions, may wander through intergalactic space. When two galaxies merge, their central black holes eventually spiral together and merge, but in rare cases the merger might produce a recoil kick strong enough to eject the resulting black hole. These rogue black holes would be nearly impossible to detect unless they happen to pass through gas that they can accrete, creating a brief flare of emission. Intermediate mass black holes, with masses between stellar mass black holes and supermassive black holes, are rare and poorly understood. A few candidates have been found in globular clusters and in some ultraluminous X-ray sources, but confirmed detections are scarce. Understanding how supermassive black holes formed in the early universe may require intermediate mass black holes as seeds. Gravitational wave detections may eventually provide stronger evidence for their existence. Black hole mergers create gravitational waves that carry away energy and angular momentum. When two black holes spiral together, they emit gravitational waves of increasing frequency and amplitude until they merge in a final burst. The resulting black hole, formed from the merger, settles down to a stable state by ringing like a struck bell, emitting gravitational waves of characteristic frequencies. Observing this ringdown allows physicists to test general relativity in the strong field regime. Neutron star mergers are thought to be the primary source of heavy elements like gold and platinum. When two neutron stars collide, they create conditions of extreme density and temperature, allowing rapid neutron capture to produce elements heavier than iron. The merger ejects material rich in these heavy elements, which then disperses into space. Kilonovae, the electromagnetic counterparts to neutron star mergers, shine brightly for a few days in optical and infrared light. The glow comes from the radioactive decay of heavy elements synthesized in the merger. The first kilonova observed in conjunction with gravitational waves in 2017 provided direct evidence that neutron star mergers produce heavy elements. These events, though rare, may account for all the gold and platinum in the universe. X-ray binaries consist of a compact object, either a neutron star or black hole, accreting matter from a companion star. As material falls toward the compact object, it heats up and emits X-rays. These systems can be incredibly bright, sometimes outshining entire galaxies in X-rays. Studying X-ray binaries helps us understand accretion physics and the properties of compact objects. Some X-ray binaries are transient, flaring up and then fading away as the accretion rate changes. Millisecond pulsars spin hundreds of times per second, their rapid rotation, the result of mass transfer from a companion star. The accreted material carries angular momentum, spinning up the neutron star to incredible speeds. Once the accretion stops, the pulsar continues to spin rapidly, losing energy very gradually over millions of years. These pulsars serve as extraordinarily stable clocks, their pulse arrival times predictable to within microseconds. Arrays of millisecond pulsars are being used to search for low-frequency gravitational waves. Pulsar timing arrays monitor the arrival times of pulses from many millisecond pulsars spread across the sky. Gravitational waves passing between Earth and the pulsars will cause correlated changes in the pulse arrival times. By comparing the timing of many pulsars, these arrays can detect gravitational waves with periods of years, far too long for ground-based detectors like LIGO. These waves might come from pairs of supermassive black holes in distant galaxies, creating a stochastic background of gravitational radiation. Soft gamma repeaters and anomalous X-ray pulsars are thought to be magnetars, neutron stars with magnetic fields quadrillions of times stronger than Earth's. These extreme magnetic fields power the emission of X-rays and occasional giant flares of gamma rays. The flares release enormous amounts of energy in seconds, briefly outshining everything else in the gamma ray sky. The magnetic field is so strong that it affects the structure of matter itself, creating strange states of matter not found anywhere else in the universe. Thorn, Fawn, Point, Cow are hypothetical hybrid stars consisting of a neutron star surrounded by an envelope of normal stellar material. They might form if a neutron star is captured by a red giant, or if a binary system evolves in a particular way. These objects would look like unusually bright red giants from the outside, but their internal structure would be completely different. A few candidates have been identified, but confirming their nature is difficult. Quasi-stars, proposed objects from the very early universe, would have consisted of a black hole embedded within a massive star. The black hole's accretion would power the star, which could grow to thousands of solar masses. These objects might have been a pathway to forming supermassive black holes in the young universe. However, quasi-stars remain hypothetical, with no confirmed observations. Understanding whether they could have existed requires detailed modeling of conditions in the early universe. Blue stragglers are stars that appear younger than they should be based on the age of their cluster. They are thought to form through stellar collisions or mass transfer in binary systems, giving them a fresh supply of hydrogen fuel. These rejuvenated stars burn hotter and bluer than they would otherwise, standing out in color. Magnitude diagrams of star clusters. Studying blue stragglers helps us understand stellar interactions and evolution in dense environments. Stellar nurseries, dense regions of gas and dust where stars form, are scattered throughout galaxies. These regions, often visible as bright nebulae, contain protostars in various stages of formation. The Eagle Nebula's Pillars of Creation is one famous example, showing towers of gas being sculpted by radiation from nearby young stars. Within these pillars, new stars are being born, hidden from optical view, but visible in infrared light. As a protostar accretes matter from a surrounding disk, it also launches powerful jets perpendicular to the disk. These jets, traveling at hundreds of kilometers per second, slam into the ambient gas, creating shock waves that heat and excite the gas. The resulting glowing knots and bow shocks mark the paths of these energetic outflows. Within the disk, dust grains stick together to form larger and larger aggregates, eventually growing into planetesimals and planets. Gaps and rings in some disks hint at the presence of forming planets, which clear out material along their orbits. Observing these disks gives us insight into how planetary systems, including our own, form and evolve. Planetary migration occurs when planets move from their formation locations to different orbits. Interactions with the protoplanetary disk or with other planets can cause a planet to spiral inward or outward. Hot Jupiters, giant planets orbiting very close to their stars, likely formed farther out and migrated inward. Understanding planetary migration is crucial for explaining the diversity of exoplanetary systems and for understanding the history of our own solar system. Is captured by a red giant, or if a binary system evolves in a particular way. These objects would look like unusually bright red giants from the outside, but their internal structure would be completely different. A few candidates have been identified, but confirming their nature is difficult. Quasi-stars, proposed objects from the very early universe, would have consisted of a black hole embedded within a massive star. The black hole's accretion would power the star, which could grow to thousands of solar masses. These objects might have been a pathway to forming supermassive black holes in the young universe. However, quasi-stars remain hypothetical, with no confirmed observations. Understanding whether they could have existed requires detailed modeling of conditions in the early universe. Blue stragglers are stars that appear younger than they should be based on the age of their cluster. They are thought to form through stellar collisions or mass transfer in binary systems, giving them a fresh supply of hydrogen fuel. These rejuvenated stars burn hotter and bluer than they would otherwise, standing out in color. Magnitude diagrams of star clusters. Studying blue stragglers helps us understand stellar interactions and evolution in dense environments. Stellar nurseries, dense regions of gas and dust where stars form, are scattered throughout galaxies. These regions, often visible as bright nebulae, contain protostars in various stages of formation. The Eagle Nebula's Pillars of Creation is one famous example, showing towers of gas being sculpted by radiation from nearby young stars. Within these pillars, new stars are being born, hidden from optical view, but visible in infrared light. Herbig Haro objects are small patches of glowing gas produced when jets from young stars collide with surrounding material. As a protostar accretes matter from a surrounding disk, it also launches powerful jets perpendicular to the disk. These jets, traveling at hundreds of kilometers per second, slam into the ambient gas, creating shock waves that heat and excite the gas. The resulting glowing knots and bow shocks mark the paths of these energetic outflows. Protoplanetary disks, the birthplaces of planets, surround young stars. These disks contain gas and dust left over from the star's formation. Within the disk, dust grains stick together to form larger and larger aggregates, eventually growing into planetesimals and planets. Gaps and rings in some disks hint at the presence of forming planets, which clear out material along their orbits. Observing these disks gives us insight into how planetary systems, including our own, form and evolve. Planetary migration occurs when planets move from their formation locations to different orbits. Interactions with the protoplanetary disk or with other planets can cause a planet to spiral inward or outward. Hot Jupiters, giant planets orbiting very close to their stars, likely formed farther out and migrated inward. Understanding planetary migration is crucial for explaining the diversity of exoplanetary systems and for understanding the history of our own solar system. The Nice model proposes that the giant planets of our solar system formed closer together than they are now and later migrated to their current positions. This migration scattered smaller bodies throughout the solar system, triggering a period of heavy bombardment that pockmarked the inner planets with craters. Jupiter's outward migration and the inward migration of Saturn eventually locked them into a resonance, stabilizing the system. This model explains many features of the solar system, from the structure of the asteroid belt to the orbits of distant objects in the Kuiper belt. The late heavy bombardment, a spike in impacts on the inner solar system that occurred about 3.9 billion years ago, may have been triggered by planetary migration. During this period, Earth, the Moon, and other inner planets were pelted by asteroids and comets. Some of this water and organic material delivered to Earth during this time may have been essential for the emergence of life. The bombardment eventually subsided as the planets settled into their current orbits and cleared out most of the remaining debris. Trojan asteroids share an orbit with a planet, sitting at stable points called Lagrange points, 60 degrees ahead of and behind the planet. Jupiter has large populations of Trojans at its L4 and L5 points, and other planets, including Earth, also have some. These asteroids are stable for billions of years, trapped by a balance of gravitational forces. Studying Trojans provides information about the early solar system, as they are pristine samples of material from that era. Centaurs, small bodies with unstable orbits between Jupiter and Neptune, are thought to be objects transitioning from the Kuiper belt to the inner solar system. Some centaurs show comet-like activity, developing tails as they approach the Sun. The Oort cloud, a vast spherical shell of icy bodies surrounding the solar system, extends halfway to the nearest star. It is the source of long-period comets, which occasionally fall inward toward the Sun. The Oort cloud contains trillions of objects, though it has never been observed directly due to the enormous distances involved. Its existence is inferred from the orbits of comets that come from all directions in the sky. The cloud formed from material ejected from the inner solar system by gravitational interactions with the giant planets. Interstellar objects, visitors from other star systems, occasionally pass through our solar system. Oumuamua, discovered in 2017, first confirmed interstellar object. Its unusual elongated shape and slight acceleration suggested it might have been an icy comet, though it showed no visible tail. Borisov, discovered in 2019, was more clearly a comet, with a composition similar to comets from our own solar system. These visitors provide direct samples of material from other planetary systems. Planetary rings are found around all 4 giant planets in our solar system, though Saturn's are by far the most spectacular. Rings form from material that is inside the Roche limit, the distance at which tidal forces from the planet overcome the self-gravity of a satellite. Within this limit, a moon cannot hold itself together and is torn apart. Ring systems are probably not permanent features, but evolve over time, with material being lost to the planet or to moons, and occasionally replenished by the disruption of new bodies. Shepherd moons are small moons that orbit near the edges of planetary rings, using their gravity to confine the ring material. Without these shepherd moons, the rings would gradually spread out and dissipate. Prometheus and Pandora shepherd Saturn's F ring, while Cordelia and Ophelia shepherd Uranus's Epsilon ring. These moons, though tiny compared to major satellites, play a crucial role in maintaining the sharp edges and intricate structures seen in planetary rings. Moonlets, small moons embedded within planetary rings, create gaps and waves in the ring material. Pan and Daphnis orbit within gaps in Saturn's rings, their gravity clearing out material and creating characteristic wake patterns. These moonlets range from a few kilometers to tens of kilometers across. Studying their interactions with the rings helps us understand orbital dynamics and the processes that might have occurred in the early solar system when planets were forming from protoplanetary disks. Resonances occur when 2 orbiting bodies have periods that are related by a ratio of small integers. These resonances can be either stabilizing or destabilizing. Conversely, the Trojans are trapped in stable resonances with Jupiter. Resonances also explain the orbits of many of Neptune's moons and the structure of planetary rings. Orbital resonances have shaped the solar system in many ways. The orbits of Pluto and Neptune are in a 3002 resonance, meaning Pluto completes 2 orbits for every 3 of Neptune's. This resonance keeps Pluto from ever getting very close to Neptune, despite their orbits crossing when viewed from above. Many other objects in the Kuiper belt are also in resonances with Neptune, evidence of the planet's gravitational influence on the outer solar system. Chaotic orbits can result from the gravitational influence of multiple bodies. The asteroid belt contains regions where small perturbations grow over time, making long-term predictions of an object's orbit impossible. This chaos explains why the asteroid belt has not remained stable over the age of the solar system, but has lost material through collisions, resonances, and ejections. Understanding chaos is essential for predicting the long-term stability of planetary systems. Lagrange points are positions in space where the gravitational forces of two large bodies and the centrifugal force of orbit balance, creating stable or quasi-stable locations. The L1, L2, and L3 points lie along the line connecting the two bodies and are unstable, requiring active control to maintain a spacecraft there. The L4 and L5 points form equilateral triangles with the two bodies and are stable, capable of trapping asteroids or spacecraft for long periods. These points are useful for space missions and are natural locations for accumulated debris. Space weather, driven by the sun's activity, affects satellites, communications, and power grids on Earth. Solar flares and coronal mass ejections send bursts of energetic particles and magnetic fields into space. When these reach Earth, they can disrupt satellite electronics, interfere with GPS signals, and induce currents in power lines that can damage transformers. Understanding and predicting space weather is increasingly important as our technology becomes more dependent on vulnerable space-based systems. The solar wind, a stream of charged particles flowing outward from the sun, fills the solar system with a tenuous plasma. This wind stretches the sun's magnetic field out into space, creating the interplanetary magnetic field. At Earth, the solar wind interacts with our magnetic field, compressing it on the sunward side and stretching it into a long tail on the night side. The boundary where the solar wind's pressure balances Earth's magnetic pressure is called the magnetopause. The heliosphere is the bubble of space dominated by the solar wind, extending far beyond the orbit of Pluto. At its outer edge, the heliopause, the solar wind meets the interstellar medium and is slowed and deflected. The shape of the heliosphere may be more complex than a simple sphere, possibly forming a tail as the sun moves through the galaxy. It was likely created by supernova explosions from massive stars that have since died. The hot gas has a temperature of about 1,000,000 degrees, but is so diffuse that it would feel like a perfect vacuum. The sun and nearby stars are moving through this bubble, which is embedded in a larger structure called the local fluff. The local interstellar cloud, or local fluff, is a small cloud of slightly denser gas through which the sun is currently passing. The solar system entered this cloud within the past several thousand years and will exit it within the next few thousand. The cloud is cool and partially ionized, with properties that affect the size and shape of the heliosphere. Studying the local fluff helps us understand the environment immediately surrounding our solar system. The galactic habitable zone is the region of a galaxy where conditions are most favorable for the development of complex life. Too close to the galactic center, and frequent supernovae and intense radiation might sterilize planets. Too far from the center, and there might not be enough heavy elements to form rocky planets. Our solar system sits comfortably within the Milky Way's habitable zone, in a region with moderate star density and sufficient heavy elements. Rare Earth hypothesis suggests that while simple microbial life might be common in the universe, complex life is rare. This hypothesis argues that many specific conditions were necessary for complex life to evolve on Earth, including a large moon to stabilize the planet's tilt, plate tectonics to regulate climate, Jupiter to deflect comets, and many others. If the hypothesis is correct, technological civilizations might be extremely rare, perhaps explaining why we have not detected any signs of them. The mediocrity principle suggests the opposite, that Earth is not special, and that life should be common throughout the universe. According to this view, The conditions that led to life on Earth are not particularly unusual, and similar conditions should exist on countless other worlds. If life arises easily given the right conditions, then the universe should be teeming with life, perhaps even intelligent life. The challenge is detecting it across the vast distances of space. Biosignatures are signs of life that might be detected in the atmospheres of exoplanets. Oxygen and methane together, for instance, would be a strong biosignature, as these gases react with each other and require continuous replenishment. Detecting such signatures requires observing exoplanet atmospheres during transits, when the planet passes in front of its star, or by directly imaging the planet and analyzing its reflected light. James Webb Space Telescope and future missions are beginning to search for these signs. The WOW signal, detected in 1977 by the Big Ear radio telescope, remains one of the most intriguing potential signals from an extraterrestrial source. The signal was strong, narrowband, and came from the direction of the constellation Sagittarius. It lasted for the full 72 seconds that the telescope observed it, then was never detected again, despite repeated searches of the same region. Whether it was a genuine signal from an alien civilization, an unknown natural phenomenon, or terrestrial interference remains a mystery. The Voyager Golden Records, carried by both Voyager spacecraft, contain sounds and images selected to portray the diversity of life and culture on Earth. The records include greetings in 55 languages, music from various cultures and eras, natural sounds, and 116 images. They are intended for any intelligent extraterrestrial life form who might find them in the distant future. The Voyagers are now in interstellar space, carrying humanity's message into the cosmic ocean. The Arecibo message, transmitted in 1974 toward the globular cluster M13, was humanity's first deliberate attempt to communicate with extraterrestrial intelligence. The message contained information about Earth, humanity, and our location in the solar system, encoded in binary. It will take about 25,000 years for the message to reach M13, and another 25,000 for any reply to return. The transmission was more a demonstration of human achievement than a serious attempt at communication. Panspermia mechanisms might distribute life throughout the galaxy, or even the universe. Microorganisms encased in rocks ejected by impacts could survive in space for millions of years, then seed new worlds when they land. On a grander scale, directed panspermia suggests that advanced civilizations might deliberately spread life to other worlds. While speculative, these ideas raise interesting questions about the origin and distribution of life in the universe. Amino acid chirality refers to the fact that these molecules come in two mirror image forms, left-handed and right-handed. Life on Earth uses exclusively left-handed amino acids, a choice that seems arbitrary. If life evolved independently elsewhere, it might use right-handed amino acids, or a mixture of both. Finding life that uses the same chirality as Earth life would suggest a common origin, perhaps via panspermia. Alternative biochemistries might exist on worlds with different conditions than Earth. Life on Earth is carbon-based and uses water as a solvent, but silicon-based life, or life using ammonia as a solvent, might be possible under different conditions. Such life would have fundamentally different chemistry, but might still exhibit the key characteristics of life, such as metabolism, reproduction, and evolution. Searching for such life requires keeping an open mind about what biosignatures might look like. The RNA world hypothesis proposes that early life was based on RNA rather than DNA and proteins. RNA can both store genetic information and catalyze chemical reactions, making it a plausible candidate for the first self-replicating molecule. The transition from an RNA world to the DNA protein world we see today would have been gradual, with DNA taking over information storage and proteins taking over catalysis. Evidence for this hypothesis includes the fact that many key cellular processes still involve RNA. Hydrothermal vents on the ocean floor create environments that might resemble where life began on Earth. These vents release hot, chemical-rich water into the cold ocean, creating gradients in temperature, pH, and chemical composition. Bacteria and archaea thrive near these vents, using chemical energy from the vent fluids rather than sunlight. Some theories propose that life originated near such vents, protected from surface bombardment and supplied with chemical energy. Lost City Hydrothermal Field, discovered in 2000, hosts carbonate towers rising from the ocean floor, powered by reactions between seawater and rocks from the mantle. The conditions at Lost City, with alkaline vents and porous mineral structures, might closely resemble the environment where life first emerged. The chimneys create natural compartments and chemical gradients that could have facilitated the formation of the first cells. The Miller-Urey experiment, conducted in 1952, demonstrated that organic molecules could form under conditions thought to resemble early Earth. By passing electric sparks through a mixture of water, methane, ammonia, and hydrogen, Miller and Urey produced amino acids and other organic compounds. While our understanding of early Earth's atmosphere has changed since then, the experiment showed that the building blocks of life can form naturally from simple chemical precursors. Stromatolites, layered structures created by microorganisms, are among the oldest evidence for life on Earth. Some stromatolites date back over 3 billion years, showing that microbial communities were established early in Earth's history. Modern stromatolites still form in a few locations, offering insight into how ancient stromatolites grew. These structures demonstrate that life has been shaping Earth's surface for most of the planet's existence. This oxygen was produced by cyanobacteria, conducting photosynthesis, slowly changing the atmosphere from oxygen-poor to oxygen-rich. The buildup of oxygen was initially slow because oxygen reacted with dissolved iron in the oceans and minerals on land. Once these sinks were saturated, oxygen accumulated in the atmosphere, fundamentally changing Earth's chemistry and enabling the evolution of complex life. Banded iron formations, alternating layers of iron-rich and iron-poor rock, formed during the period when oxygen was beginning to accumulate. When cyanobacteria produced oxygen, it reacted with dissolved iron in the oceans, forming iron oxides that sank to the bottom. Variations in oxygen production created the banding pattern. These formations, found on every continent, are not only evidence of ancient microbial activity, but also the source of much of the iron ore mined today. The Cambrian explosion, about 540 million years ago, saw a rapid diversification of animal life. Within a geologically brief period, most major animal groups appeared in the fossil record. The causes of this explosion are debated, but likely include rising oxygen levels, the evolution of predator-prey relationships, and the development of hard body parts that fossilize more easily. The Cambrian represents a watershed moment in the history of life on Earth. Mass extinctions have punctuated Earth's history, with 5 major events recognized in the fossil record. These extinctions, caused by various factors including asteroid impacts, volcanic eruptions, and climate change, killed off large percentages of species. Yet they also created opportunities for surviving groups to diversify and fill empty ecological niches. The recovery after each mass extinction reshaped the biosphere, leading to the emergence of new dominant groups. The Permian-Triassic extinction, about 252 million years ago, was the most severe mass extinction known, killing perhaps 95% of marine species and 70% of terrestrial species. Massive volcanic eruptions in Siberia released enormous amounts of carbon dioxide and other gases, triggering climate change, ocean acidification, and widespread anoxia. The recovery took millions of years, but it paved the way for the age of dinosaurs. The Cretaceous-Paleogene extinction, 66 million years ago, ended the reign of the dinosaurs. An asteroid about 6 miles in diameter struck what is now the Yucatan Peninsula, creating the Chicxulub crater. The impact released energy equivalent to billions of nuclear bombs, triggering wildfires, tsunamis, and a global winter as dust and soot blocked sunlight. Non-avian dinosaurs went extinct, along with many other species, but mammals and birds survived and eventually diversified into the forms we see today. The Chicxulub crater, now buried beneath sediment, was discovered through careful analysis of geological and geophysical data. The impact site shows characteristic features including shocked quartz, high concentrations of iridium, and a layer of spherules representing material ejected from the crater. Drilling into the crater has provided samples from the impact layer, offering direct evidence of the catastrophe that reshaped life on Earth. Snowball. Earth episodes, periods when Earth's surface was entirely or nearly entirely frozen, occurred several times in the distant past. During these episodes, glaciers reached the equator and the oceans froze over, creating a planet that would have been almost unrecognizable. Life survived in refuges such as hot springs or thin ice that allowed some sunlight through. The end of each snowball episode came when volcanic carbon dioxide built up in the atmosphere, eventually warming the planet enough to melt the ice. Continental drift, the slow movement of Earth's continents, is driven by plate tectonics. The continents have wandered across the globe over hundreds of millions of years, sometimes joining together into supercontinents and sometimes fragmenting. Pangaea, the most recent supercontinent, began to break apart about 200 million years ago. Before Pangaea there was Rodinia, and before that, other supercontinents we know less about. This cycle of assembly and breakup continues today. Plate boundaries come in 3 types: divergent boundaries where plates move apart, convergent boundaries where plates collide, and transform boundaries where plates slide past each other. Each type creates characteristic geological features. Divergent boundaries create mid-ocean ridges and rift valleys. Convergent boundaries create mountain ranges and subduction zones, and transform boundaries create faults like the San Andreas. These boundaries are where most of Earth's earthquakes and volcanic activity occurs. Subduction zones, where one tectonic plate slides beneath another, are sites of intense geological activity. The descending plate releases water into the overlying mantle, lowering its melting point and creating magma that rises to form volcanic arcs. Subduction zones also produce the planet's most powerful earthquakes. The deepest parts of the ocean, the trenches, form where plates subduct. Over millions of years, subduction recycles oceanic crust back into the mantle, helping to regulate Earth's long-term climate. The Ring of Fire, a region encircling the Pacific Ocean, contains most of Earth's active volcanoes and experiences frequent earthquakes. The Ring of Fire demonstrates the connection between plate tectonics and surface geology, showing how the movement of plates deep beneath the surface manifests in dramatic ways at the surface. Mantle plumes, columns of hot rock rising from deep in the mantle, create hotspots that can produce volcanoes far from plate boundaries. Hawaii sits over a mantle plume, and as the Pacific plate moves over the stationary plume, it creates a chain of volcanic islands. The Big Island of Hawaii is currently over the plume and is volcanically active, while older islands to the northwest are extinct and eroding. Mantle plumes provide a window into processes occurring deep within Earth. Magnetic reversals, when Earth's magnetic field flips polarity, have occurred many times throughout Earth's history. These reversals are recorded in rocks, particularly in oceanic crust formed at mid-ocean ridges. The pattern of magnetic stripes in the ocean floor was key evidence for plate tectonics and seafloor spreading. The inner core of Earth, a solid ball of iron and nickel about 1,500 miles in diameter, crystallizes from the liquid outer core. Despite temperatures hot enough to melt iron, the immense pressure at the center of the planet keeps the inner core solid. The inner core rotates slightly faster than the rest of the planet, an effect detected by analyzing earthquake waves that pass through it. Understanding the inner core helps us understand Earth's magnetic field and the planet's thermal evolution. The outer core, a layer of liquid iron and nickel surrounding the inner core, generates Earth's magnetic field through convective motion. Heat escaping from the core drives this convection, creating electric currents that produce magnetic fields. This geodynamo has operated for billions of years, protecting Earth from harmful solar radiation. Without it, Earth's atmosphere might have been stripped away by the solar wind, as happened to Mars. The mantle, making up most of Earth's volume, slowly flows in a process called mantle convection. Hot material rises from near the core mantle boundary, spreads horizontally beneath the crust, cools, and sinks back down. This convection drives plate tectonics at the surface. The mantle is solid rock, but over geological timescales it flows like a very viscous fluid. Understanding mantle dynamics is crucial for understanding Earth's thermal and geological evolution. Oceanic crust forms at mid-ocean ridges and is recycled at subduction zones, making it relatively young, usually less than 200 million years old. Continental crust, by contrast, includes rocks billions of years old, preserving a record of ancient geological processes. The difference in density between the two types of crust is why continents stand higher than ocean basins. They have survived multiple cycles of mountain building and erosion, preserving information about the early Earth. Studying these ancient rocks reveals that plate tectonics may have begun early in Earth's history and that liquid water existed on the surface by that time. These rocks also contain some of the oldest evidence for life, including possible microfossils and chemical signatures. Zircon crystals, extremely durable minerals that can survive erosion and recycling, have been dated to over 4 billion years. These tiny crystals, found in younger rocks, are pieces of Earth's earliest crust. Chemical analysis of zircons suggests that liquid water existed on Earth's surface by 4 billion years ago, much earlier than previously thought. Zircons provide our oldest direct samples of Earth's material. The late veneer hypothesis proposes that much of Earth's water and precious metals were delivered after the moon-forming impact by a late influx of asteroids and comets. The moon-forming impact would have been so energetic that it likely vaporized Earth's existing water and drove off volatile elements. The late veneer arriving afterward brought new supplies of water and metals like gold and platinum. This hypothesis helps explain why these materials are more abundant on Earth than expected. The Moon's origin is best explained by the giant impact hypothesis, which proposes that a Mars-sized object collided with Earth early in its history. The impact ejected material that coalesced to form the Moon. Evidence for this includes the Moon's composition. which is similar to Earth's mantle, and its relative lack of iron compared to Earth. Computer simulations of the impact can reproduce the Earth. Moon system's key properties supporting this dramatic origin story. Tidal locking of the Moon means it always shows the same face to Earth, a result of tidal forces that slowed its rotation until it matched its orbital period. The far side of the Moon, hidden from Earth, was a mystery until spacecraft photographed it. The far side has fewer maria, the dark basaltic plains that cover much of the near side. This asymmetry may result from the Moon's offset center of mass or differences in crustal thickness, but its exact cause remains debated. Lunar mascons, concentrations of mass beneath the Moon's surface, create local gravitational anomalies. These mascons are found beneath impact basins and are thought to be dense material from the mantle that welled up after the impacts. They affect the orbits of spacecraft around the Moon and provide clues about the Moon's internal structure and the processes that occurred after large impacts. Transient lunar phenomena, brief flashes of light or color on the Moon's surface, have been reported by observers for centuries. Most reports come from areas of recent volcanic activity, suggesting they might be caused by outgassing from the lunar interior. However, these phenomena are rare and poorly documented, making them difficult to study. Whether they represent real lunar activity or observational artifacts remains uncertain. As our journey through these mysteries comes to a gentle close, we find ourselves back where we started, looking up at the night sky with a sense of wonder. Each answer we find leads to new questions. Each discovery opens up new realms of mystery. From the smallest quantum particles to the largest structures spanning billions of light years, from the beginning of time to its potential end, the cosmos invites us to explore, to question, and to dream. And in that ongoing exploration, we find not only knowledge, but also a profound connection to something greater than ourselves, a reminder that we are part of this magnificent, mysterious universe.